This coordinate plane shows a composite waveform tracking amplitude over time. The math driving it, a specific combination of three distinct cosine functions, creates a jagged, almost chaotic pattern on a standard graph. Physical signals in the real world rarely exist as a single pure tone. When you pluck a heavy steel guitar string, the metal vibrates at multiple intersecting frequencies simultaneously, generating overlapping standing waves in physical space. If we strictly observe these events on a chronological timeline, just watching the amplitude rise and fall second by second, we obscure the actual forces at play. The true structure of the wave is hidden behind the resulting collision of those components. To solve real engineering problems, like designing circuits to handle complex alternating current loads, we have to isolate those individual variables. We need to know exactly which underlying frequencies are driving the system. This requires completely changing our analytical perspective. Instead of asking when an event happens, we have to ask how fast it cycles. Moving away from a time-based view and entering the frequency domain allows us to decode the physical reality of a signal. It turns a chaotic mess into a structured, readable map. The mechanism for this shift relies on a specific mathematical rule. Any continuous periodic waveform, no matter how complex, is actually a linear combination of basic sine and cosine waves. This framework was formalized by French mathematician Joseph Fourier in the early 19th century. His method gives us a clear set of objectives. First, we take a discrete, repeating signal and mathematically fracture it into exact trigonometric components. Next, we take those isolated components and plot them visually, creating a distinct frequency barcode that catalogs every oscillating part. Finally, we apply this logic beyond simple repeating loops, using Parseval's theorem to analyze isolated, non-repeating signals and measure their total physical energy. Fourier's decomposition is not a mathematical approximation. It is an exact extraction process that reveals the deterministic fingerprint of a signal. This graph shows the composite signal we looked at earlier. You can clearly see the complexity and the jagged peaks of a single line tracking amplitude over time. Fourier's trigonometric series splits this line into a vertical stack of three separate cosine waves. Comparing these plots isolates their defining parameters. Distinct peak heights dictate amplitude, wave widths indicate frequency, and horizontal offset shows the precise phase shift. While this trigonometric form, using variables a and b, is valid, managing separate sine and cosine equations becomes computationally tedious for large systems. To solve this efficiency problem, engineers use Euler's relation to convert the math from standard trigonometry into a complex exponential series. This packages amplitude and phase into a single complex coefficient, amplitude divided by 2 multiplied by Euler's number raised to the phase angle. This calculation produces a mathematical byproduct. Each real cosine wave splits into two symmetrical components, representing positive and negative frequencies across the complex plane. Adopting complex exponentials gives us a mathematically complete mapping of the signal, consolidating two trigonometric variables into one elegant expression. These positive and negative components translate into a discrete visual spectrum. In the top magnitude line spectrum, specific vertical spikes appear at exactly 1, 4, and 8 radians per second. Their height measures the absolute amplitude of each specific frequency. The three constituent frequencies we isolated earlier correspond perfectly to these paired spikes on the graph. Magnitude alone leaves a blind spot. Different waveforms can share identical magnitude spectrums if their components start at different times. That is why we need the bottom phase line spectrum chart, dictating the specific time alignment for each frequency. By tracking how much each frequency is shifted horizontally, we can see exactly how the components lock together to create a specific physical shape. Magnitude shows what is present, phase shows how it aligns. Together, they form the unique frequency fingerprint required to reconstruct the physical signal. The pure mathematics of the Fourier series assume we can sum an infinite number of harmonic frequencies. But in practical engineering, calculating infinity is impossible. Real-world signal reconstruction relies on a partial sum, deliberately capping the calculation at a finite number of harmonics, designated by the variable n. This chart shows how sequentially increasing that harmonic count affects the output. As we move from n equals 3 to 5 and down to 59, the addition of more sinusoidal layers progressively tightens and smooths the approximation of this continuous triangle wave. But watch what happens when we apply that same process to a discontinuous signal, like a rigid square wave. Notice how high-frequency ripple artifacts appear precisely at the sharp vertical step edges. This chart isolates the boundary error, the Gibbs phenomenon. As the harmonic calculation expands from n equals 19 to 59 to 199, the ripples compress horizontally, but a 9% amplitude overshoot stubbornly persists at the central transition point. A perfectly vertical edge requires an instantaneous change. Since mathematically smooth sinusoids take time to curve, they can never perfectly resolve an infinite physical discontinuity. This establishes a hard limitation on discrete harmonic reconstruction. The Fourier series has operated under one strict boundary condition. The time domain signal being analyzed must repeat infinitely in a periodic loop. To analyze an isolated, non-repeating signal, we treat the solitary event as if it does repeat, but with a period stretching out to infinity. Because frequency is inversely proportional to the period, as that time period extends toward infinity, the spacing between the harmonic frequencies shrinks toward zero. As those frequencies compress, the gaps on the discrete line spectrum vanish. The vertical bars squeeze horizontally closer together until their peaks merge entirely, forming a solid, continuous envelope curve. This transition, moving from the discrete summation of specific harmonics to the continuous integration of all possible frequencies, is the Fourier Transform. This table shows standard Fourier Transform pairs. Because this mathematical relationship is fixed, specific time domain shapes translate directly into pre-calculated continuous frequency domain equations. The Fourier Transform liberates our analysis from repeating loops, giving engineers the mathematical tools to decode any isolated, singular physical event. We have taken tangible signals recorded in time and fractured them into abstract frequency components across a complex plane. This raises a critical physical question. Does mathematically shifting a signal into this abstract domain alter its actual measurable energy? Parseval's theorem proves it does not. If you calculate the average power by measuring the area under a squared waveform in the time domain, you get a specific value. Parseval demonstrated that you calculate the exact same total average power simply by squaring and summing the absolute values of the discrete harmonic coefficients. And when we extend this logic to aperiodic Fourier transforms, the mathematical equivalence holds steady. For an isolated event, total signal energy is found by integrating the complete area under that continuous spectral density curve. Whether you measure the event chronologically as it happens, or sum its constituent frequencies as a whole, the resulting numerical value is identical. Time and frequency are strictly just two mathematical lenses used to view the exact same reality. The analytical perspective changes, but the physical energy of the system remains strictly conserved.